Good evening, everybody. I am so pleased to welcome you to this evening's special session with the public lecture, which will be given by 2018 Nobel Laureate Donna Strickland. My name is Meta Garda. I am from Louisiana State University, and I am also chair-elect of DAMOP, and I will be your chair for this evening session. So before we get started with the public lecture, we have a few DAMOP members to honor. So Dad will present the DAMOP, the APS fellowships given to DAMOP members, and then we will have a presentation of the Deborah Ginn Thesis Prize for AMO Research that happens in the next few minutes. So with that, I'm going to hand over to Dad.
Thank you, Meta. It is a real pleasure to recognize our 2021 DAMOP APS Fellows. The Fellowship Committee you see there on the slide, they always report the highly competitive nature of these fellowships, and so it's a real honor to win them. So I'm going to read off the names and citation, and when I read your name, the recipient, you can come up and receive your certificate and pin from Meta. So the first one is Ashish Clark, and I think I've already messed up. I apologize for the pronunciation there. For fundamental contributions to the theory of quantum optomechanical systems, quantum dissipation engineering, and other areas of quantum optics. The second awardee tonight is Andrew Daly, University of Strathclyde, for pioneering theoretical work on the boundary between quantum optics, many-body physics, and for experiments in both atomic, molecular, and optical physics and the solid state. Our next awardee is Superdeep Gupta, University of Washington, for outstanding contributions in the areas of ultracold quantum gas mixtures, atom optics, and atom interferometry, I'm pretty sure. Our next recipient is Mohammed Hafezi, University of Maryland, for pioneering theoretical and experimental work in topological photonics and quantum synthetic matter. The next one is Liang Zhang, the University of Chicago Pritzker School of Molecular Engineering. He's receiving it for innovative theoretical contributions opening new directions in quantum communication, computation, and metrology. Next is Alexander Kromita, National Institute of Standards and Technology, for developing highly effective methods for uncertainty quantification and for the evaluation of atomic spectroscopic data and its efficient dissemination through the world's most reliable atomic databases. The next one I saw today, so Benjamin L. Lev from Stanford University for groundbreaking experiments on quantum gases of lanthanide atoms with large magnetic dipole moments, theoretically proposing and experimentally demonstrating many-body multimode cavity QED for many-body physics, and the demonstration of novel scanning quantum gas imaging of quantum materials. And finally, our last recipient is Monica Schleier-Smith from Stanford for pioneering experimental and theoretical contributions to quantum measurements and quantum simulation with ultra-cold atoms. As you're only too aware, the last 2 years we have not met in person. And so our APS fellows for those years were only recognized virtually. I wanted to take a moment to recognize them tonight. Here you see the list of 2020 APS fellows: Martin Centurion, Alexander Cronin, James Cryan, Alexei Gorshkov, Corinna Kolyath, Dominic Schnabel, Deborah Watson, Thorsten Weber, and Jonathan Weinstein. And if any of those are in the audience tonight, we'd love for you to stand and so we can acknowledge you. Likewise, our 2019 DAMOP APS fellows were Jens Biegert, Yu Ao Chen, Xueng Wang Du, Francesca Ferlano, Eric Hudson, Matthias Kling, Dmitry Romanov, and Jing Zhang. And if any of those are in the audience, please stand and so we can acknowledge you. Apparently, the real pleasure in getting these awards is doing the work. So it really is a huge honor to become an APS fellow. We congratulate the new and old fellows this evening. I'd like now to turn the podium over to Wes Campbell, who will present the Deborah Ginn Prize.
Okay, thank you, Thad. On behalf of the award committee, it is my pleasure to present the 2022 Deborah Ginn Award for Outstanding Doctoral Thesis Research in Atomic, Molecular, or Optical Physics. This award is endowed by M-squared lasers, recognizes doctoral thesis research of outstanding quality and achievement in AMO physics, and encourages effective written and oral presentation of research results. Deborah Ginn was a distinguished AMO experimentalist known to all of us for her pioneering work in degenerate Fermi gases and ultra-cold molecules. After her passing in 2016 at the age of 47, her colleagues, friends, and family honored her contributions to research and mentorship through an additional endowment of the award. This year, my fellow award committee members are Caden Hazard, Bob Jones, Monica Schleier-Smith, Tanya Zolovinsky, and I'd also like to extend special thanks to Hossein Sadigpour and Albert Stolo for serving on the committee in the first round of the selection process. We received 23 fantastic nominations. That is not an exaggeration. They were really pretty incredible. The committee thanks the members of DAMOP for their support, encouragement, and nomination of these 23 individuals as outstanding scientists at the forefront of a new generation of AMO physicists. From the nominations, the Thesis Prize Committee selected 4 finalists. It was extremely hard to do that step, by the way. It was not fun, but we had to do it. And before we announce the overall winner, I'll introduce the 4 finalists in the order in which they presented. So when I call your name, please stand. We'll get a chance to recognize you with a good round of applause. It's going to be well-deserved. They were all incredible presentations. And if you could stay standing until we have all 4 of you announced, and then folks can sit back down and I can announce the overall winner who will maybe come up to the front, and Gordon, if you'd be willing to take their photo, we'll get a photo of you. We don't have one of those golf tournament checks for you, but my understanding is that a smaller check is also part of the finalist prize. Okay. So our first presenter today was Annabelle Bourne for her thesis entitled One, Two, Many Holes, New Insights into the Doped Fermi-Hubbard Model. Let's thank Annabelle. Our next presenter is Luke Caldwell, his thesis entitled Deep Laser Cooling and Coherent Control of Molecules. Harry Levine for his thesis entitled Quantum Information Processing and Quantum Simulation with Programmable Rydberg Atom Arrays. And Ofer Neufeld for his thesis, Novel Chirality and Symmetry Properties of Light and Their Utilization for Ultrafast Spectroscopy. And I can say that these were my four favorite talks that I saw here at DAMOP, and I know a lot of you share that same sentiment, so excellent job by all four of the finalists. In what is always one of the most anticipated and well-attended invited sessions at DAMOP meeting, these four finalists gave incredible presentations. If you attended the session, you can certainly understand that the final selection process was no easy task for the committee. It was awful. But congratulations once again to our four finalists. We can recognize them as they sit back down. And finally, it is my pleasure to announce the overall winner, whom I asked to come up to the stage and get a photo. And the winner of the Deborah Ginn DAMOP Thesis Award for 2022 is Harry Levine.
Wes, shake his hand.
Cool. All right, let's thank all four finalists.
I now invite David Haneke, the chair of the GPMFC, to present the poster prize.
Thank you very much, Thad. So the topical group on precision measurements and fundamental constants. Each year at DAMOP, we highlight young scientists pursuing high precision work with goals such as finding beyond the standard model physics or creating new methods of sensing forces or measuring time or other precision measurement tasks. This year we had 9 poster entries. They were at the Tuesday evening poster session, and I hope you had a chance to look at them. They were really, really fantastic. So our poster prize committee was tasked with selecting 2 winners, and the selection criteria was based on the intellectual merit of the work, the innovation of the research, the impact on the field, and the quality of the visual and verbal presentation. So each winner will receive a check, another small one, and since we just decided today we don't have the check, it'll be in the mail, and there'll be a certificate too. But if I announce you, please come up. We'll have another picture and a handshake. So the 2022 GPMFC poster prize winners are Con Leung from Columbia University, whose poster was Molecular Vibrational Spectroscopy with 13-digit accuracy. and Nia Burrell from Northwestern University, whose poster was ultra-sensitive force sensing with optically levitating nanoparticles. So congratulations to you both.
All right, that concludes our prize session, and I'll now turn it over to Meta.
Thank you. I wanted to tell those of you who are standing up in the back, there are lots of seats in the front and over in this section if anybody wants to come and sit down. And now I am very pleased and honored to introduce tonight's public speaker, Dr. Donna Strickland from the University of Waterloo. Donna was one of the recipients of the 2018 Nobel Prize, which was given for groundbreaking innovations in the field of laser physics. And in particular, half of the prize was awarded to Gerard Mourou and Donna Strickland for their method of generating high-intensity, ultra-short optical pulses, which is what Donna is going to tell us about soon. You may know that Donna is only one of 4 women ever to be given the Nobel Prize in Physics. This is definitely a trend we hope to continue. And so it is truly an inspiration for us to have you here with us today, sharing your work and your experiences. As another point of inspiration, maybe especially for the students in the audience, the prize-winning work was published in 1985 while Donna was a PhD student at the University of Rochester, and Gerard Mourou was her supervisor. So just think about that when you are working all those long hours and the experiment is not working. You never know. She has since then gone on to have a distinguished career with many, many awards and distinguished. So for instance, some of them are up here. She was president of Optica, formerly the OSA, in 2013. She's a fellow of many different societies. She's an international member of the National Academy of Sciences, and many other things that I will not read out loud to you. The title of Donna's talk, as you can see, is From Nonlinear Optics to High-Intensity Laser Physics. As you all know, it was the development of the laser that allowed a huge increase in the intensity of the light that can be brought to interact with the physical system. And what Donna is going to talk about is the development of so-called chirped pulse amplification, which allowed for another huge increase in intensity and is the basis for all high-power laser systems around the world. And so it feels extra special for me as a representative of the strong field and ultrafast laser community to welcome you here today. So this is just a reminder. So as we get started, there is no recording of this talk allowed. If there's any members of the media present, you can record the first 5 minutes, but nothing else. And then please help me welcome Donna Strickland to the stage. We're excited to hear what you have to say.
Okay, so I guess I gave that title before I saw that I was giving a public talk. But I have to say, so this is my public talk, and it's a public talk about atomic and molecular physics, and optical physics, of course. And I feel very strange giving a public talk on something that you guys are all experts on. So I hope there's the odd person in the room that's not an AMO physicist, because otherwise this is kind of weird. But anyway, just know that this is the public talk. This is mostly my Nobel lecture that I gave, and so it is for the general public, because I'm going to explain what a photon is to you people. And you know, that's up for debate. All right, so the other thing, though, is that what's really lovely to see at this conference is how many young people and graduate students there are because the unofficial title of this talk is What Did I Do for my PhD that landed me the Nobel Prize? When I spoke at the APS March meeting, both Gerard and I were there for that meeting, and what was really funny, I thought, was that all the gray-haired people like us lined up to meet Gerard afterwards, and all the students lined up to meet me, because I've sort of become not only the woman who won physics, but I am sort of the now icon of what you can do with your PhD. One of the questions, though, that I got asked a lot was, do I have advice on how to do an award-winning PhD? And I do not. It just takes a lot of luck. So I'm sorry I can't pass that on. So let's get started on my talk. It's also a story really about the importance of doing pure or basic or fundamental research, depending on what you want to call it, science for the sake of science, and applied research, because I think you need both to keep moving forward. And so that's what this talk's about, is that we went from linear optics to nonlinear optics when the laser was invented, but we couldn't have invented the laser without understanding linear optics. And then it was nonlinear optics that stopped us from putting short pulses into amplifiers, and so we had to understand that so that we could work around it. And when we got CPA, we went from nonlinear optics to high-intensity laser physics. And so it changed again how light and matter interacts. And so it is the fact that we have to go back and forth and have both to keep moving a field forward. All right, so this is the level of my talk. So to understand why I needed to build a high-intensity laser, and let me say, why was I Gerard's student that got to do this Nobel Prize-winning work, is that I was his 7th student, and I was the first one to need a high-intensity laser because I was the first one going to do a high-intensity laser experiment. Everybody else was building short-pulse lasers to do fast experiments. That's why I am the lucky one that got to do it. So, but we can't understand it without actually first understanding the linear interaction between light and matter. And I am going to use the photoelectric effect, 1, because that's why Einstein won his Nobel Prize, and 2, because in the end, as we meander through my PhD thesis, you'll see that I did the multi-photon version of that for my PhD. So back in the middle of the 19th century, scientists were still trying to figure out if light is a particle or light is a wave. And there was reason to think both, right? And so it was, of course, as we know, Maxwell that convinced scientists that absolutely light should be a wave. Now, as an experimentalist, though, I'll also say, and Nobel agrees, that you have to see it experimentally for it really to be true. So experimentalists then had to figure out how are we really going to prove that light's a wave. And so I'm going to talk about light that we see. The longest wavelength we see is red. Green is the one we see the best, and violet is the shortest that we see. We don't quite see an octave of light, right? So it's not quite a factor of 2. So the wavelength is the distance between the crests. So the experimentalists came up with this experiment, and it's analogous to if you can walk along a stony beach. Now, we're here in Orlando, Florida, so we're not far from a beach, but we're about as far as you can be and be in Florida. But hopefully you've all had the chance to walk on a stony beach. And so you know that if you're walking on a beach and the waves are just little ripples, the stones don't move. But when the waves come crashing in, of course, the stones get shoved up the beach. And so we all know, without being physicists, that the power in a wave comes from the height of the wave, not the distance between the crests. So the experiment that they came up with was, let's shine light on the material and watch the electrons come off in a completely analogous way to stones on a beach. And they'll turn up the power, and they'll watch those electrons fly off even faster. Now, since we're all AMO, and maybe somebody should almost put up their hand if you're not an AMO, so I could talk right to you. But anyway, so then they turned up the light, and it didn't matter with red light, electrons never came off. With green light, it came off at low speed, and when they turned up the power, more electrons came off, but always at that same low speed. And finally, when they used violet light, that's when the electrons came off at high speed. So these experiments really flew in the face of light being a wave, and people had to think about it again. So it is Albert Einstein, I've already said that this is what he won the Nobel Prize for. Now, I'm just back from 3 weeks in Texas, and I was with an atomic and molecular group there, and they argued with me quite a bit after my talk, and I gave the physics version. So now on the physics version, I also put Planck on this slide. But anyway, I haven't for the public. We're just going to go with Albert Einstein and the fact that he's the one who figured out these experiments. And basically, it's the fact that by this time they already knew that the energy of electrons and atoms were quantized, but this showed that the light should be quantized. Of course, Planck also showed it. The light is also quantized. And so the minimum energy unit is what we call the photon. The photon is a wave-like particle. I think that's the best we can explain it, but there's probably people here that would argue with me on that one too. But let's go with that. So now, what was also then shown, more by Planck than by Einstein, is that the energy of this single photon is given by its color or its wavelength. So I explained the photoelectric effect now using the analogy of playing basketball with a child-sized basketball net. And so we're going to start with the red photons. And so the red photons, because the energy goes with the frequency, or the inverse of the wavelength, red photons are like your child-sized photons. So even if they're, with the child-sized basketball net on their tippy toes, they still cannot dunk the ball through the rim of the basketball net, and this is why no electrons come off. Now, when you turn up the power in the photon picture, you are turning up the density of the photons. So it's like you had a lot more of those child-sized photons all around the basketball net, and still none of them can get their balls through the net. But green photons are like adult-sized photons. That's playing with a child-sized net, and I only play basketball with a child-sized net myself. So they actually can, get their balls through the net, but only at low speed, because there's hardly any difference between where they're dropping it and when it gets through the net. Again, when you turn up the power, you are letting more of those green photons all around the net, and they're all dropping their electrons through the net, but at that same low speed. And then the violet ones are your pro basketball playing. Now, when I'm outside North America, I do explain that means they're tall people, but I think here in the United States, you probably know that. So these are the tall photons, and when they play, then the balls go through at high speed. So this explains the photoelectric effect. When we teach it to the undergrads, we usually are teaching the quantum mechanics of it. But for this talk, I want you to concentrate on the fact that this is an example of a linear optical effect. And what I mean by that is that it is always one photon interacting with one atom at a time. And if that photon has more energy than what the atom is holding onto its electron, then the electron goes off with the difference in energy, because as we know, energy is never created nor destroyed. And so it's linear. If you turned up the power, you would have more photons interacting with more atoms, but it's still one photon interacting with one atom at a time. If you double the power, you'd have twice as many electrons go off, and so it's twice the power now in the electrons, but at that same speed. Okay, so that's where we were at the beginning of the 20th century, and I'm guessing at that time the scientists thought they pretty much had light-matter interaction all locked up. And then along comes this woman, Maria Gopimer. Now, she is famous for being the second woman to win a Nobel Prize in physics, but that's for work she did at Argonne National Lab in the 50s. But when she was still a graduate student, she started this whole new field of physics called multi-photon physics. She was the one who asked the question, why do atoms only absorb one photon's worth of energy at a time? Why can't an atom absorb two photons? So I'm showing it here with my going towards multi-photon ionization. She did two-photon absorption. But again, if you could absorb the energy of two photons, then with my basketball example, it would be like two red photons, and so it wouldn't even be violet, it would be ultraviolet, but there's no point in drawing it as ultraviolet. None of us would see it. So there it is. So it would act like twice the energy was absorbed. So she worked out the semi-classical treatment of all of this, and showed it. It's a sole author. She was a graduate student working with Max Born, and it's a sole author paper that came out in 1931 to explain this. It wasn't until 1961 until we had the first demonstration experimentally. Now, I'll also say that two-photon absorption, which is what she talked about, was also seen in 1960, but that came out a few months after this one. Now, this one is not called multi-photon physics, it's called nonlinear optics. And I'm just going to tell you what a slow learner I am. I had worked in the field for 25 years and did not know there was a difference between nonlinear optics and multi-photon physics. And then I was at a meeting called 50 Years of Nonlinear Optics. And Pierre Agostini got up, who's the father of ATI, and he goes, I don't know why I'm here speaking about nonlinear optics, since that's not what I do. And I was left going, really? Because, like, what would you say you do? So just in case you don't know the difference, because it took me so long, and there may be some of you like me, if you're an atomic or molecular physicist, you do multi-photon physics. But if you're an optics person and watch what happens to the light, then you're doing nonlinear optics. And it was just too subtle for me to notice. So the first one that was seen was nonlinear optics because it was a light thing. And so what did this Michigan group do? This Michigan group had a material that simultaneously absorbed 2 red photons, but it didn't hang on to it, it didn't cause ionization, but it released the energy, not as 2 red photons, but as 1 ultraviolet photon. And so this is second harmonic generation. All right. I want to also say, just in case, because so many of you are young, and now everybody under the age of 40 looks really young to me, so I don't know how young you are, but just so you know, Peter Franken was the first author on this paper, but that's because this work was really done by a 4th-year undergrad for his undergrad thesis project. So I just think, isn't that an amazing undergrad thesis project? And that was Hill. His last name was Hill. Okay, so we saw it in 1961. Maria Gopimer told us we should have seen it in 1931, and so that begs the question, why did it take 30 years before anybody could see it? And as I've already said, we needed to have the laser come along in 1960. So this is my Nobel talk, and I do want to pay homage to all of the Nobel Prize winners that went ahead of me in my field. And so Basov and Prokhorov were working together in Russia. Charles Towns was working independently in the United States. The 3 of them developed the maser. The maser is the precursor to the laser, where M stands for microwaves and L stands for light. Technologically, it was easier to make a maser than a laser, and so that was done in the 50s. Art Chawla won a few years later for laser spectroscopy. He's one of the people who helped figure out how to get the technology to work for lasers. But it's really this guy, Ted Maiman, working at Hughes Aircraft. He was the one who first figured out how to make a laser work, and it was demonstrated on May 16th, 1960. I've been waiting to celebrate the 60th anniversary on May 16th, and it's been canceled now 3 times because of COVID. Anyway, so that's it. That happened in 1960, and that's why we saw nonlinear optics by 1961. So what makes a laser so special? And we all know that it is. So the light that's very bright, almost blinding me, shining on me, is very, very bright light, but it's still putting light in all directions. That's why I'm all lit up. It's also, you see me in living color, because every color photon is coming out of that bright light. But most importantly, the photons coming out of that light don't care what each other are doing. They're just all doing their own thing, and this is what we call incoherence. Now, unlike that, with my laser pointer, which you can almost see on the screens, you will see it's a nice tight beam. It's a single color. But most importantly, the photons coming from this all care what each other are doing. So when one crests, they all crest, and then they all trough, and then they all crest. And in this way, you can build up a giant wave. And so this is why the light is so much more intense coming out of a laser. So why did that help nonlinear optics? So the main point really is that you have to actually cram more than 1 photon into the interaction volume of the atom if you want to simultaneously absorb 2 photons. Now with regular light, like we're seeing here, you will see that the photons are all dancing to their own beat because they're all different colors. They also don't care how the other photons are dancing, so they simply can't crowd on to that dance floor very well. Now, we could try to squeeze them together by using a lens, And it might look like you can focus down to a point, but we all know you can't focus to smaller than the wavelength. This is about 1 micron. And 1 micron seems small when you think the size of the human hair is 50 microns. But as we know, the atoms are 10,000 times smaller than that. And so it's virtually impossible with these regular light to see more than 1 photon in this interaction volume. And since we are AMO physicists, I will point out that the interaction volume is the cross-sectional area, and the third dimension is the interaction time. I kind of think this is why Maria Gopimer chose 2-photon absorption to study, because it would be a resonant effect, and so it would have the longest interaction time and should be the strongest effect. On the other hand, to see it, you have to use a secondary measurement. All right, but with the laser, now Nicholas Bloomberg won his Nobel Prize for laser spectroscopy with Art Shallow, but he's sort of considered like the father of nonlinear optics, like Maria Gopimer is considered the mother of multi-photon physics, so their parents have sort of twins there. So now you'll see that all of the photons are dancing together. They not only all dance into the same beat, but they actually all dance together. And this is why they can crowd onto that dance floor. And that's why in 1961, they were able to see in one shot, in 1 million to 10 million, the 2 photons being absorbed by the atom. So what has any of this got to do with me? And it was because when I joined Gerard's group, he gave me this paper written by Stephen Harris, a professor at Stanford, who had written a theoretical paper in 1973. I don't know why Gerard was all of a sudden looking at it, because it would have been 1981 or early 82 when he gave it to me. But it was about, the idea was, that's great that we have lasers in the visible and we have lasers in the infrared, but wouldn't it be fantastic if we could get this coherent radiation up into the XUV and onto the X-rays? And there will be many of you still trying to do that, right? So he came up with some schemes to use even order resonances to get to high order, odd order harmonics. So he had all the way up to the 15th order, and again, I can't draw XUV, or you wouldn't see it. So Gerard said, think about it, see if this is what you want to do for your PhD, and if you do, think of a way to make it happen. So I decided it would be something fun to do, and we had a YAG laser, and I came up with an 8th order resonance to allow a 9th harmonic in twice ionized nickel. So there was going to be 2 parts to my PhD. I was going to need to make a cold plasma of twice ionized nickel. It has to be cold because you have to have all of them in the ground state of that twice ionized nickel. And I was going to need an intense laser pulse, because I didn't want just 2 or 3 photons in that volume. I wanted 9 photons in that volume. And so I needed to figure out a way to make a really intense laser. So I had these 2 parts to my PhD thesis, and only one of them worked. Luckily, one of them worked really well, because the other one was a total dud. Okay, so I never did do harmonic generation, and near the end, I'll tell you another reason why it would have been silly to do it. Anyway, but that's what I thought I was going to do. But let's talk about the successful part. I also want to point out to students that a lot of people will talk about how it was my very first paper that won me the Nobel Prize. But you have to remember, I started my PhD in 1981, and my first paper came out in 1985. So I had a whole lot of failures before I had my one success. Okay, so how did I get a really intense laser? So this is something that, to this day, I've been working with lasers for 40 years, and I still am amazed by this. I can make a 1-second light pulse. Here, I'm just going to do it on the wall behind me. And where's my camera? I should do it for the camera. Here we go. And you can just make a 1-second light pulse pretty easily. Now let's assume that we have a glass ceiling, and not the proverbial one, a glass ceiling right above us. And let's assume the moon is out there. I have no idea where the moon is. Right? And I do this 1-second light pulse. Sorry, those watching, you can't see it, but you can imagine what I'm doing. And so I do this 1-second light pulse, and it gets more than 2/3 of the way to the moon before I shut the pulse off. I still find that amazing that light travels so fast. You know, when I fly here, how many hours did it take just to get from Toronto to here? So the other thing I labeled there is 1 millijoule of energy. So then why do I have 1 millijoule listed? One, that's all the energy there was in that 1985 paper, so that's about my work. But also, if you look at the pointer I'm using, because it should be eye safe, it should be roughly about 1 milliwatt of power and no more. And that means with power being energy per unit time, that every second I have 1 millijoule of energy hitting my hand, okay? Now, if I hold this light up to my hand, and I try to hold it still, but my hands shake a lot, I can almost feel my hand warm up. So 1 millijoule doesn't seem like much, does it? But that's all you need to cut glass or to cut the cornea of your eye with a CPA laser, and it only has to be 1 millijoule. So the question is, what's the difference? And the difference, again, is that photon volume. So the 1 millijoule of energy that comes out of this laser pointer is strung out over a 300,000 kilometer line, which is a very long line of light. Now, that first experiment that was done in 1961, there it goes, used a millisecond laser pulse, because this is actually the original lasers had to be pulsed to get the energy in there. So that's still, though, 300 kilometers. So it's still pretty long. I'll also say it was 1 joule of energy. So it was 1,000,000 times more dense than what I'm holding on to here. And that got us 2 photons in 1 part to 1,000,000 to 10 million. I wanted 9 photons, and I hopefully wanted it more efficiently than that. And so what we did was actually get all the energy into 1 picosecond of time. So instead of having the energy of this little laser stretched out over 300,000 kilometers, all of that energy, or all of those photons, were squeezed down to 1/3 of a millimeter. I like to say that I built a laser hammer. Sometimes it's energy that matters, and sometimes, just like driving a nail into a piece of wood, you can push with all your might, but then when you pick up a hammer, it goes in. So it just depends on what you want, but if you want a laser hammer, you want the energy, and you want it squeezed down to a short pulse. So let's see how I did it. We're going to go back to Earth here, and we're going to go to Rochester, New York, where I did my PhD. And there I am as a young student. And I'm at the Laboratory for Laser Energetics, which is a Department of Energy funded facility for laser fusion. So a fellow Canadian that met me my first week in Rochester found out I wanted to study lasers, and he said, I know where you want to go and who you want to work with. And the very next day, he took me over to meet Gerard Moreau, and he took me into this lab. And I just saw, obviously I wasn't wearing goggles because I saw the red and green, and just thought, oh my goodness, it would be like working around a Christmas tree all year long. How much fun would that be? Now, I never did get to use that laser, but that's beside the point. I joined the group. Now, this is an example. It was already there when I joined the group. It's 100 femtoseconds. So it's 10 times shorter, or it's all in a 30th of a millimeter. So we had really short pulse lasers, but it was a dye laser. And a dye laser, as I will explain later, is not a laser that can be made into a big energy. So we have short pulse lasers. Right across the lobby of the LLE was this. This was the main reason for LLE. It is a laser fusion facility. Laser fusion is an application that does require energy. Energy in gives you the energy out. So just to give you a little bit of a scale here, this laser sits on basically a football-sized field of all one optical bench there that's been poured. And this object right here is the size of a human adult, okay, just to give you a scale of what these big lasers are. This is a 1 kilojoule, so 1,000,000 times more energy than what comes out of this every second. So at the Laboratory for Laser Energetics, we had big energy lasers, and we had short pulse lasers, but we couldn't put them together. Now, those of you who do work with lasers would say, well, obviously you can't put a dye laser into a glass because it's different wavelengths. That's true. But people had tried to put short pulses at 1 micron down these glass lasers. And what they found out, although they probably didn't call it that in those days, is that they had a laser hammer inside their laser. And sure enough, holes were drilled right down the center of those rods. And so that made one whole group of people go, oh, I wonder why that's happening, because they would go in with a big beam, and yet you get these tiny holes all the way down the center of the rod. So the nonlinear optics people went off and studied what the heck was happening. Laser jocks like me just said, don't put short pulses down big energy systems because you caused an awful lot of expensive damage. Just don't do it. So that's where we were into the mid-1980s. And so this is George's and my Nobel. And so in 2019, I pointed out that this is the first color photo, and that's because, you know, the rest were history. But of course, I should turn this one into black and white, because George and I are history now, too. So anyway, I also want to point out that I think of all the Nobel Prizes in physics, I've got the easiest one to explain. So here it is. I want a laser hammer. What's a laser hammer? A lot of energy in a short pulse of time. I don't want that laser hammer inside my amplifier destroying it. So very simply, you start with a short pulse oscillator, you stretch it, you make it a long pulse, you go ahead and safely amplify that long pulse so the power stays low, and then when it's safely out of the amplifier, you go ahead and compress it and have your laser hammer ready for your experiment. Now with our 1 millijoule, and even when we went up to 100 millijoules, we were okay compressing in air. Today's big systems will compress in vacuum because even air is a nonlinear medium at these biggest intensities. So that's it. Now we could have called it stretched pulse amplification, but chirped pulse sounds better. We did use dispersion, which means that we have the different colors separated in time through the pulses. And so this is the same as a bird's chirp, only that's an audio frequency changing in time through the chirp. And so that's why it's called chirped pulse amplification. So how did I do it? So this looks like it's the very same laser I already showed you before, but now it's not called a dye laser, it's called a neodymium YAG laser. Remember, I was going to do 9th harmonic of YAG, and it was going to be this YAG. So it's back here. This is the YAG, and it's a 1 micron laser into the near infrared, or infrared, and that's why you don't see any beam coming out. This object here is a frequency doubler. Now, this is the same kind of object that was used by the Franken group, where they only had a part in a million to 10 million conversion. But now the intensity of that YAG laser was enough to get 10% conversion to the green. For those of you who don't use lasers, I don't know how many AMO people don't use lasers, but anyway, our mirrors really actually are very good to reflect the colors we want it to reflect, and then absolutely no good for the other colors. And that meant this is a 2-watt neodymium YAG. We converted to about 200 milliwatts of green, and most of that 2 watts then went right through this mirror into a beam dump, okay? And we could always tell when somebody walked into the beam, especially the one guy who always wore a wool sports coat. That really smells when the beam hits that. Okay, so you'll also see that there isn't very much room here for me, and even though that's the laser I'm going to use. So here I am, 1984. I know it's still 1984 because both ends of my fiber stretcher are in the same room. And I could not, there was no room in this lab left for me. And so there's actually 3 uses for the fiber that you see there coiled up. And one is that once we got the light through the fiber, my colleague, my fellow grad student, who was not as claustrophobic or as afraid of heights as I am, very nicely, even though it had nothing to do with her project, she crawled through the air duct one middle of the night, because you're not technically allowed to do this, and strung the fiber to the other end of the laboratory for laser energetics, where they did now have cleaned up, emptied out lab for me to build the rest of CPA. Because this is my public talk, I'm not going to explain that we did use nonlinear optics, self-phase modulation in the fiber, because the YAG was 150 picoseconds, and we wanted it to be closer to 1 picosecond. I will also say, because I was given the physics version of this talk, 1984 was when fiber pulse compression was all the rage. And that's why, as soon as we saw that at the Ultrafast conference that year and Clio that year, Gerard had the idea for CPA in 1983. But when we saw that work, we went, oh, it's going to happen. And now we know how to do it, and we got to do it now. So we use it for self-phase modulation, but it is really the stretcher. So I'm going to tell you why it's 1.4 kilometers, because that is 1.4 kilometers of fiber. And early in 2019, I was giving this talk at the University of Toronto, and I know there's some Toronto people here. And she asked the question about, did I do the calculation and figure out that it needed to be 1.4 kilometers? And then I gave her the answer, and I just saw this terrible disappointment. And I could tell she was sitting there going, you won a Nobel Prize. You should have had to figure something out. So let me tell you why I have 1.4 kilometers, because this is also a good story for, I think, all grad students to understand. I've just said that once George wanted it done, he wanted it done now. So there was no writing proposals, getting the money to do this experiment. So the amplifier I used was actually one he had used back in France for his PhD, and he had it shipped over. The oscillator, I said, was already there in the lab. And so he called down to Corning, which is just an hour south of Rochester, big glass company, and they were doing the fibers for optical communications. And they are the ones who had come up with this specialty fiber for this pulse compression of neodymium lasers. Now, the other word for specialty fiber, as you will know, is expensive fiber. And he called and he said, this is going to be a really important piece of work. Don't you want to be involved with it? And don't you want to donate fiber for the project? And Corning very generously donated 2.5 kilometers. Now, I guess that most people that want 2.5 kilometers of fiber want to lay it down across 2.5 kilometers because only one end was showing. And you will see that I have both ends there that I need to get to. And so I had to spend a day of my life unspooling and respooling, but we only had that one spool. So we had a film canister that we laid corks, glued corks around, and I just did this for a day. And then we tried to put the light through the fiber, and it didn't go up through. So as Murphy's Law would have it, I had nicked the fiber pretty much in the middle. And so the bigger of the two halves was 1.4 kilometers, which I did measure by counting the number of times I looped it. And so that's why. So I could have done the calculation, which I didn't have to because they'd already done that for the fiber pulse compression. I already knew what I needed. And 2.5 kilometers wasn't quite long enough anyway. So what the heck? You just keep going forward. We had no fiber splicing. We didn't even have fiber cleaving. I had to do it with a diamond knife in my hand. That's how I did it back in the day. So anyway, that's why it's 1.4 kilometers, and it was good enough. It worked. All right. So how does the stretching work? You need a lot of colors. So even though this laser that I'm showing you is single color, if you can see one color, and I'm going to try to see green. But anyway, it would go on and on and on. And I'm sure we all know our Fourier transform theory. It is not the Heisenberg uncertainty principle, people. That what you need is a lot of colors. If you say that there's one point in space and time where all the colors have to peak, then as you go away from that peak, the colors, of course, the peaks, start coming away from each other. And at some point, there's as many peaks above as there is below. And that's how you make a short pulse. And the more colors you bring in, the better you are. We have something in our lasers called a mode locker. So a mode locker does the same thing as a conductor of an orchestra. When we all go and listen to an orchestra warming up, they sound terrible because they, again, are like an incoherent light. They don't care what their neighbors are doing. They're all listening at their own instrument, playing their own notes when they want to. And so they're like a light bulb. But when the conductor brings down his baton and they all play their notes together and make beautiful music, that's what we have in our laser. It's a mode locker, and it says, everyone go. I will also show that this is a Fourier transform limited pulse, as done by PowerPoint, that you will see they are equally spaced crests. And so if you truly have the shortest pulse, it's Fourier transform limited, so it looks like it's a single frequency with an envelope. That's ideally what we want. Not what I had, but ideally what we want. All right, so now we have all those colors. How do we get them to disperse? I started this talk about talking about quantum levels and that photons have a certain energy. We're not talking about ionization. We're going through glass fiber, which means that it's transparent, and that means the energies are well above these colors. But if it's up here in the ultraviolet and the red photon comes along, they talk to each other and go, we got nothing in common. So they hardly speak together at all. The green starts to wonder, and by the time it gets to blue, it says we could almost be friends. We're so close, but not quite. And that's why the red light, runs through the glass, the green walks, and the blue crawls. And so at the end of my 1.4 kilometers of fiber, I had 350 picoseconds. I wanted a nanosecond. I needed a nanosecond. I will also say that when I did sometimes turn up the power all the way, I did damage, and I did see those beautiful long streaks of damage. But anyway, when I was careful, I didn't damage them too often. So Ideally, we would have stretched, and today, they would, if they're using glass, they will stretch to a nanosecond. Okay, so that's our stretch pulse. So now I'm actually going to explain how a laser works to all you people. So I don't know if Linda Young is here or not. I think the first time I said this, I was in Chicago, and she did tell me that she was insulted. But I'm going to insult her again anyway. Because after that, just recently, I think it really is subconsciously true. So of AMO, I will say I'm really an optical physicist and not an AM physicist. And so you will notice that in my slides, only the photons have personality. And that's how you know these are atoms. They have no personality, OK? So these are the atoms, and they're just sitting there in their ground state, so they need to be excited. So you're going to put in some kind of energy, and for the egg or the glass amplifier, that would be a UV, XUV, or a UV lamp. OK, if you've engineered it well, you will have most of your atoms sitting up in its excited state. Now, I told you early on, dye lasers do not have storage energy capacity, and that's because it's a high-gain material. It actually does not want to stay in its excited state. It's going to start spontaneously emitting all directions, and it becomes, if you make it too big, it's going to be a light bulb. It will not store the energy. But glass is one of the biggest stored energies, and it will sit around and wait a long time, by laser standards, for a photon to come along. So now, see, there's my photon with its personality, but they are the very same color. And so what Einstein showed us in 1917 is that stimulated emission would happen the same as absorption. And the beauty is that it will take the energy and it'll walk hand in hand. Okay, they will be coherent with each other. Those two will meet two more atoms, and they will take the energy, and the 4 will become 8. This is the way all lasers begin. They begin with one noise photon going down the pipe of the laser, and it takes off. This is the exponential gain region, but you can see when you're in the exponential gain region that you have left most of the energy behind. And so it's totally inefficient to do it this way. And so what you want, and this is one of the reasons there's a cavity around a laser to send the beam back and forth and back and forth. Now, this is Florida, so it's not a good analogy. So you just have to imagine vacationing in Canada where we have snow plows. But it's like a snow plow is what you want, where you just go and take all the energy. And so you do have to get up to what's known as the saturation energy flux. And that's when you're in this linear, energy efficient way of pulling out the energy. So this glass has got one of the biggest. It's 5 joules per square centimeter. So this is why that glass laser that's a kilojoule is large. You start with an oscillator. It will be a very tiny beam because it's got to start from 1 photon, and you eventually get up to that 5 joules per square centimeter in a tiny beam. You then make the beam a little bit bigger, go into an amplifier. Each stage, you make it big enough that it just goes in with that 5 joules per square centimeter into the next one, until eventually, if you want a kilojoule, you need a pretty big beam. Okay? So that's what you do. And so for glass, you know that you want to go in with 5 joules per square centimeter. Every material has its nonlinear optical coefficient. That's the one that says you have to make sure the photon density stays below this if you don't want the beam to collapse due to nonlinear optical effects. And so that's why for glass, it had to be stretched to be a nanosecond. This is the one time American units work. Nanosecond is exactly a foot. So I know what a nanosecond is. OK, so a nanosecond, so you really want your pulse to be stretched out like this. And so that's what all you need to do to calculate how much stretching you need. And the last stage then is compression. Like prisms that send colors in different directions, we have optical gradients that do it even more than prisms. And so we're going to use 2 parallel gratings so that all the beams will come off parallel to the way they start. If you watch the red photon, which is out ahead of the green photon, out ahead of the blue photon, you're going to see that red bends the most. And so it will travel, and as it comes off, it will have traveled, the red line will be as long as the blue line. Okay? And so it comes off as a short pulse. Now, again, so many of you will be laser people here, so let me point out that, of course, it's a line, and so the gradients are half that distance apart, and we retro it back, and it becomes a round beam and compressed. So that's the whole thing. So by the time I was done, I had no way of measuring. So I set up the compressor with just the oscillator stretching and compressing, because we had autocorrelators that could do that. But I did not have a way, it was a 10 hertz system, and how to measure a single shot that was short at the time. But luckily, my friend and colleague, Steve Williamson, had just gotten himself a fancy-dancy new street camera, and he wheeled it in one night, and we worked one Thursday night into the wee hours, and with an Edelon to calibrate his street camera, and showed that we did indeed have still the 2 picoseconds. When I compressed it just with the oscillator, it was 1.5 picoseconds, and this is limited by the 4 pixels, and so it worked. It was one happy night. All right, so I had the laser, and actually Patrick Main came along and helped me build 2 more amplifiers. So it isn't with a millijoule that I do this experiment. I already said I never did figure out how to make cold plasma of twice ionized nickel. I will also say by the end of my PhD, which was 7 years long, a French group had already seen the 33rd harmonic. So it was like, why even try to see the 9th when there's already people doing the 33rd? Okay, so it made no sense. So lucky for me, Silong Chin had come down from the University of Laval because he had heard about the CPA system, and he wanted to be the first person to use it, and he wanted to study multi-photon ionization. And so he convinced Gerard to let me do multi-photon ionization for my PhD. So, and he was trying to see, is it tunnel ionization or multi-photon? That's for those of you who work in the field. So multi-photon ionization would be, instead of talking about playing basketball net, we're going to say, okay, the electron is way down in this well, and we have to give it enough energy to get out of the well. With the IR photons we were going to use, it was going to take about 11 of them to get out of a xenon and send it on its way. It would have to have gone with the 11th order of power, and it did not. And it didn't actually even follow tunnel ionization. I will say, just in case anybody knows Phil Buxbaum and knows him well, he was the reviewer of the paper. We did not actually understand our results. And it was the reviewer, who I now know is Phil Buxbaum, who actually replotted the data for us and showed that what our data showed was that, forget the photon picture, we now have the photon density so high that you could go back just to that classical wave, which then knocks over the well, and it was over the barrier ionization. Now, my colleague, the fellow grad student who worked on this with me, I was just seeing he's now at Lincoln Labs, and I'm telling this story, and I'm looking at him going, how come we didn't put Phil Buxbaum's name on the paper if he's the one who figured it out? And he said, we asked. He said no. But I'm just telling you, Phil Buxbaum was the one who figured this out. So that's the end of my PhD, but let me just show a picture going forward. Gerard has been showing this picture for quite a number of years. It used to be more vertical than horizontal. It's a sort of intensity as a function of year. So the laser came along in 1960, and really, I have no idea how low it was before that. Q switching and mode locking are 2 techniques to make the pulses shorter. And this is what I talked about. We could not take those short pulses and amplify them, and CPA came along in 1985. Livermore was the first place to successfully take one of those kilojoule lasers and do CPA with the kilojoule laser in a picosecond and get the petawatt. Okay? It took 10 years. 5 years was Gerard asking everybody in the world to do it. And I think most people being a little afraid of those great, big, very, very expensive glass rods. The other 5 years, though, it took Livermore 5 years to work on how to build the gratings. So we had a 1 joule system that we showed that we could amplify to 1 joule, but our gratings could only handle 100 millijoules, and that's why we did the experiments of multi-photon with 100 millijoules. And so this was a 5-year project to not only figure out how to make large gratings that had these perfect rulings, because if you go to do perfect compression, you have to know you have perfect rulings, but that also could get, my gratings were 50 millijoules per square centimeter, and they got it up to 1 joule per square centimeter. And I think almost all of the big lasers still use Livermore gratings to this day. This is Gerard's own laser. It's actually a little bit less powerful than the one at Livermore when he was at Michigan. But they were the ones who used adaptive optics that had been developed by the astronomy community, and to take out the phases from all the thermal problems of the amplifiers and actually focus down to single wavelength dimensions. And so that's how they got to 10 to the 21 watts per square centimeter back in, I don't know when. I don't know, sometime in the 2000s. So the last 2 have just been added by me, and since I didn't make this curve, I don't know how to curve over the dotted line. But the blue is blue and not black because this is the most powerful laser in the world. It's at Eli in Europe. It's 10 petawatts. So it is actually that same kilojoule now with 100 femtoseconds, okay? Or is it 10 kilojoules in a picosecond? I should know. I was there for the grand opening, but only on Zoom. Anyway, 10 petawatts. So they have not, as far as I know, done a focused intensity. The leading one is in Korea. It's a 4 petawatt laser, and they have also now focused it down using the same techniques that Gerard did, down to single wavelength, and so they're at 10 to the 23 watts per centimeter. But I do like to point out to all students that we have once again rolled over, and it is time for another Nobel Prize winning idea to kick us on up again. Because when Gerard first started showing these pictures and it was much more vertical, he thought by now we'd be up in this orange region. This is past the Schwinger limit. This is the idea that we could then take our light and focus it into vacuum, and out would come matter and antimatter, because the force at that focus would be the same as the force holding the electron and the positrons together in the vacuum. So we're waiting for that, but we need a really good idea to kick us on up. I'm going to take us back down now to finish this talk at the blue part and just talk about the practical applications of CPA. If you want, you can see really cool videos about laser machining steel. This is a linear effect, though. This is absorption. This is taking the energy and converting it into heat and then just basically melting or sublimating the steel right off, okay? And so you can only cut such fine holes because you are dealing with heat and it will have to dissipate. What I have here is a laser hammer, and you're going to hammer it. Now, we also then don't have to talk about linear absorption, right? And so then the question is, can we cut glass? Because obviously, I can take my glasses off and the beam goes right through. So it's not absorbing the light. And so there's a couple of advantages now to using CPA, because it's only right at the focal spot that you're going to have that laser hammer. So now you don't have to, like you do with steel, cut from the edge. You can leave the beam big at the edge of your cornea or the edge of a piece of glass and focus inside that transparent object and do the cutting inside. So I'm going to show you now the video of the corneal surgery. If you're squeamish, don't watch. It's taken me a long time to be able to watch this. Now, I can't remember if I had to click again. I guess I have to click again. Oh, here we go. I'm docking, I'm sure, is some medical thing. I have no idea. I'm sure it's about holding your eye still. I would have the surgery if you could be like asleep for it, but you have to stay awake. And it's not even the laser. Here comes the laser. It's going to scan at 1 kilohertz. It's going to take 17 seconds. And it looks like it's damaging the outside, but that is where your nerves are. And that is why a flap is created for LASIK surgery. It is still an excimer that reshapes your cornea, but this is just to cut the flap. So this is the part, if you're squeamish, don't watch. And this is why I can't imagine lying there, because now the surgeon's going to come and attack the eye with his tweezers to lift that flap up. That's the part that's hard to watch. All I've learned to do it. There it is. See, that's why I think, no way am I going to have that surgery. I can wear glasses. But you're going to see what a nice cut it does. Still about half of them use scalpels, so you don't have to use a laser. But there it is. So that's it. So that's the end of the science. I'm just, if there's time, someone tell me if I have no time, I'm just going to run through a little bit of Nobel Week. Because it is, the Nobel ceremony is actually a 4-hour television show that is shown around the world. But, you know, and they actually come and they spend a day with you. It's a day in the life of a Nobel laureate. You know, they take me getting in and out of my car, going to work and whatever. I had to make coffee for them because Gerard made coffee for them. And when they were there, I said, well, no, we don't see the TV show here in North America. You know, no, we don't actually watch the Nobel ceremony. We watch the Oscars and the Grammys, but we don't do that. So anyway, so I'm just going to show you a little bit. It is quite a spectacular ceremony. We do have a royal family sitting here. This is the king with his wife, the queen, the crown princess. I also want to explain how EDI Sweden is, because years ago, when her younger brother was just 2 and he was the crown prince, they said, you know what? No way. It's going to be the firstborn. Boy or girl, doesn't matter. And so she was the firstborn, so she became the crown princess. And luckily, the brother was only 2, so I guess he didn't know. Her husband is sitting behind. The rest of the royal family is sitting in the front row. The red chairs here are the current crop of laureates. Unfortunately, Art Ashkin had found out he got cancer just about a week after the announcement, and so he was unable to join us. His son, Michael, came, but he didn't get to sit in a red chair because he's not a Nobel laureate. The people behind us are previous laureates. These are the members of the various Swedish academies that pick us. I love this woman's dress. She was from literature. It was supposed to be her last year. My year was the year that nobody got it in literature because of all the scandals, so I think she was really making a statement. The flowers are sent from an Italian town, and when we went for our practice at 10:30, we could not take pictures and show it to people because it all has to be a surprise for everybody, but it is sent from the town where he would winter at the end of his life every year at this town in Italy. There's a music played for us in between each of the prizes, and you'll see this is the end where we practice. So this starts at 3 in the afternoon, but at 10:30 in the morning, we come, and in our book, we have a whole book for whole Nobel week to tell us where we have to be, how we have to be dressed, what we're doing. And this was one of the times, 10:30 sharp, we had to be there to learn how to take the medal from the king's hand. And I read that, and I went, what does that mean? Am I not allowed to touch the king? Like, what do we do? So I will show you what we practice. But one of the things we practice is to walk up. When you see the king come with yours to the end, you know it's your turn to walk to the end. But I'll show. So here Gerard and I standing. We're standing first because I think we all know in physics that in the Nobel's will, he put physics first, and so physics always comes first. I also want to point out that I was supposed to go back in 2020 and be one of these people, but it didn't happen in 2020. But I did tell myself that I have to keep a smile on my face because these two guys don't look very happy that CPA won. Okay? I don't know if they're really that unhappy or that's just the way they always look. But anyway, you never know when the camera's on you. So, all right, so that's us. And here I am, smiling because I've just won. So now let me tell you what, you will see that inside this portfolio is both a piece of art that's just for me. So the 3 physics ones were done by the same artist, so they're similar, but they're not the same. So I have my own unique piece of art. I have my certificate inside there. The gold medal is inside this box. And so what you practice is that there's a pretend king. He doesn't come to the rehearsal. And he's got the folder by 2 corners, and he brings it to you, and you take the other 2 corners, which I'm holding, and the box is sitting in the middle. And this king has been doing it for many years now, knows very expertly how to, with his thumb, move it, so, and you lift up your thumb, and he makes sure that you've really got a good hold of that, because it's kind of heavy, that metal. Hold it, and then he lets go of his 2 corners. He then steps back, and that's your signal to then bow to the king. And then you turn with your back to the audience and bow to the Royal Swedish Academies, and then here I am, either ready to bow or finishing bowing. And I do like to point out why I'm smiling. Most people will think it's because I've just won the Nobel Prize. But this is what a woman is thinking about. That dress was so unbelievably tight. The whole time I was thinking, what happens if that dress splits open while I'm bowing to the Royal Swedish Academy? And so I'm just glad to be through the whole thing. Okay. So that's the end of the ceremony, and then this happens at the Royal Concert Hall, and then we go to Stockholm City Hall for the banquet. And so here we are starting to line up, and you will see some people, Gerard has his invitation, my husband has his invitation, I think George Smith is putting his away. In this invitation, we were each given 2 numbers. So my husband and I, our first number is 2, and then he got number 14, and I got number 1. So we're 2 because Gerard and his wife are 1, because it's physics first. I think I've made that clear. Physics first, and then it's alphabetical. But Art Ashkin would have been first, but they wouldn't let his son is there, but he always had to go 10th, okay? I also want to point out, because this is a TV show shown in Europe, that because all French women, so Gerard's wife was walking the red carpet, she was dressed by the House of Dior. She was given jewels to wear. I was asked who I was wearing for the TV show. I went, no, I had to go to a department store and buy it myself. No one gets free advertising. So that's just one of the differences between being North American. And somehow Frances had to buy her very fancy gown too, but she made some comment at a TV show and somebody sent her a box. So the other days she was wearing clothes sent to her, but this one she bought herself too, because she's North American. All right, so what are we doing there? We're standing, and when I actually gave this talk for the first time, the public talk, it was at the University of Waterloo, and my sister came, and she was with me in Sweden as well, and I called this the gold room, and later she said, Donna, that wasn't the gold room. The gold room was around the corner. That's where the ball was. And I went, oh my goodness, you're right. Stockholm City Hall has a room that's even golder than this room. It's actually got, I guess, gilded with gold, the other room, and this just looks gold. All right, so what are we doing here? So we're all going to be at the center table. We are all going to be greeted by the royal family who will come through this door and meet us one at a time. When they get past us, these people with their white hats are going to take you to the second number. And so you'd see that my husband, who had 14, is sitting here, but I was given number 1. So why was I given number 1? Physics is first. And by Royal Swedish protocol, you always dine boy, girl, and so I'm the one who got to walk in with the king. Now, you may wonder, what would a nerd like me say to a king? Because how often does one meet a king? I will tell you what I'm saying here. And who knows me, I do not like to walk slow. And we had to walk like it was even slower than a wedding march, all right? And I'm sitting there, and I know I'm saying it to him right then. See, all the other royals knew exactly where the cameras were. But anyways, I'm saying it's killing me to walk this slow. And because it's not being taped, right, I'm going to tell you, the king, charming, very charming, said, I agree with you. I say something every year, but who listens to me? And there I am, having the time of my life at a banquet, talking to a king. Now, this time, I knew where the cameras were because there were about 10 or more right there, and he's looking at one, I'm looking at the other, but we're having a blast. So that's the end of December 10th, 2018. Your 14 guests go home, but you and your spouse get invited to the palace to dine with the royal family. The other one is run by the Nobel Foundation. This one is run by the royal family. This time, they line up, and you walk in one couple at a time, and then these 3 move aside and make this gap that you go into and get this photo. This was my dinner companion that night. He was the other prince, crown prince, but now he's just a regular old prince. But even when my husband's in the audience, I point out that no TV Prince Charming can do anything on this guy. This guy is the real deal. He really was the most charming man I've ever met. So he was my dinner companion, and where did we dine? This is the dining room of the palace. I'm in the center there. I'm across from the king. And I just remember sitting in this incredible dining room with Prince Charming on my side, thinking, how did I go from just trying to do a good PhD to landing in the middle of a fairy tale? But that's where I was. And finally, the week ends on the 13th when you go and you get back. So they take away the medal and stuff. You don't go to the banquet having to carry this stuff. And the artwork is actually on display in the ballroom during the banquet, or during the ball. So this is it's in a box, the other part, and here's my medal again. And you also get the money that day. And they ask you to sign this register. Now, before they have you sign the register, they show you other people that have signed the names, the signatures. And for, I think, all physicists, they opened it up to Albert Einstein's signature first. And for me, they showed me Marie Curie and Maria Gopimer. I mean, and then I looked through the whole book, but then they say, now it's your turn. And it has to be the most surreal moment of my life. I could not believe I was signing the same book as those legends of the field. So that's the end of the week and the end of my talk, and thank you very much. Good. Is it time for questions? It's all right, it's up to you. Don't take my picture now.
Thank you, Donna, for this wonderful talk. Donna will take some questions. Usual format, please walk up to the microphone if you have a question.
Hey, Donna, thank you for a great talk. Just a quick question. Why did you use a fiber for the pulse stretching and not a
Grating.
A grating? Yes, because the one that we have uses a grating. We don't
course.
have that, so I was just wondering
That
why.
is another common question I get by you young people. So let me explain. Oscar Martinez had not invented the pulse grating stretcher until 1987.
Gotcha. Okay.
And this was 1984 going into 85.
Gotcha. Thank you.
Okay. I told you they'd all understand it.
Cool. Very good.
I have
Thank
sort
you.
of a meta question. In the spirit of having a public lecture, I was wondering what's the most insightful or interesting question you've ever received from a member of the public?
I know the oddest question, but I just don't think I should say it. Well, actually, the last one, so I was just in Seattle, where I just saw somebody get their fellowship there. And they had a lot of questions for me after that public talk. That was actually a real public, I think. And they had missed understanding why it needed CPA for glass. And so that made me rethink how I give the talk, and I decided I would show the light going through the glass and talk about it. So I actually do look for questions like that keep making the talk a little bit better, because it is the 100th time. Although I have to say, when I gave the talk at McGill, it was funny, because a young woman got up and she said, "You seemed very poised giving that talk. Can you explain how you were so poised to give the talk?" I said, "I think it's because it's the 50th time that I've given the talk. So if you can't be poised after 50 times, when can you?" So that was it. But I won't. No, are you taping, not taping? Should I say what the weird question was?
Not taping.
Well, maybe I shouldn't say that. What if the woman's in the room? I won't say where it was done, because that might cue it. I gave a talk. It was the public talk, and again, it was for a public. And she said that she really enjoyed the talk, and did I have advice to give to her that she could give to men to say how it is that you should give a talk that women can understand. And I found that very strange. So I will say that was the strangest question I ever got. I pointed out that my favorite Nobel lecturer is Bill Phillips, and it's a guy, and I understood it. I didn't quite say it that way, but that one I found strange. So.
Hi, Donna. I have a question. I'm a PhD student in the second year. I want to know if you have any suggestions for, a PhD student.
That your advisor doesn't have? Is that what you're saying to me? Other than, and this is what, and I even said this, I will tell you that when I joined the group, there were 7 of us, and by the time I was finished, there were 30 of us in Gerard's group. And I think we really exploded because this is, again, you're so young, it was Reagan Star Wars, so you have to, A, know who Reagan is, and B, know that one of his big things was this idea that lasers would blow up Russian missiles. And so a lot of money was spent on that. And it really brought people into the laser business because there was just so many laser jobs. I can tell you that the one year at Clio, I went into the women's bathroom, of which, there's very few of us using the bathrooms at Clio in those days. And the one woman said, "Are you Donna Strickland?" And I went, "Yes." And she goes, "Oh, I'm with Rocketdyne. We have jobs." I went, "Well, okay, but I'm a Canadian, and so there you go." But a lot of the people that joined Gerard's group did not have the real joy of doing it, okay? And there were, not all of them, but just some of them, I would ask, I said, "Why are you in Gerard's group? Because you don't really seem to love this." And she's going, "Well, because it'll be a good job." He or she, both males and females said, "Well, because there'll be good jobs." I said, "We're here for 7 or 8 years. You don't know what the job market's going to be. And I can tell you, after the end of my postdoc in '91, there was hardly a job to be found." So I was right about that. And so this is always my advice. It was my advice for students when I was a student. It's still my advice. You really got to do what you love. Because if you do what you love, it's worth doing, even if you don't get a job at the end. But I also think that you really, if you put your heart and soul into something, you do it the best. And that's all you can really hope to do, is do your best. And so that's what I would always say. Make sure it's something you really want to do.
So, Donna, I have a question about would you be willing to talk to students in smaller groups afterwards? So if you are not comfortable standing up in front of everybody, then there will be a small reception outside afterwards. But please, if anybody else has a question they want.
But if you're old, apparently you have to have the nerve to ask me anything. And obviously I say anything, so.
Oh, we have another one.
Hi, Donna. You said something interesting in your talk about how your advisor, Gerard, made an effort to not make you go through the whole proposal process and really making sure and just going and doing the experiment. And I was curious if you've used that philosophy in your own group and if you feel like the landscape has changed a little bit in terms of writing proposals versus just going and doing it.
Well, you have to have the wherewithal. I mean, you have to do something to get everything there. So let me just say a few things about that. I mean, obviously, Gerard, had the chutzpah. I don't think I would have the chutzpah to call Corneal and say, don't you want to donate a fiber? That's, I think, my big problem. Gerard had chutzpah that I just did not, and I still do not. But others do. I've talked to other people, and they're very good at just calling up people, and they get things, so I should have some more chutzpah. So that's one thing. Two, we also had a very good electronics engineer. And so actually, this very old laser that he brought from France, I remember my husband actually changed the name of it to go with Marcel. I'm trying to think what the name of the actual laser was. But anyway, he had to fix it so much that if you didn't have that kind of engineer, it'd be hard to do with this 20-year-old laser or something, right? Or 10-year-old laser. We did have to buy the gradients, though. That was the one thing that we had to buy. So again, we were at the DOE-funded facility. And so they were able to cough up some money. And so it ended up being sort of this joint project then. And so the experiments were then done as one of the big lasers now at the DOE facility. So he had some things to play at, but he certainly had an old laser he could scoff at. He had the chutzpah to ask Corning to donate 2.5 kilometers of expensive fiber, and he had the laser lab to back him up to give him the one thing that we needed to buy. And the egg laser is something that we just used because it was going to waste. So that part I would do, okay? That part I would make sure I figured out.
Thanks.
Hi, Donna. So I have also a question. I don't know exactly how to phrase it, but many times, I think it's come out, let's say, the argument that you're a woman winning a Nobel Prize. And I'm curious now to understand, is it something, that you are proud of, let's say, of this underlining the gender aspect, is something that you see as an opportunity to, build up an example, or is something that kind of annoy you that it's always stressed out? Thank you.
I already told you I'll be honest about it. First of all, it surprised me. I find it a very hard hat to wear to be this woman STEM role model because I actually never noticed the whole way through that it was a problem. And yet I don't want to minimize all the problems that women have had. But I just don't, people want advice from me, and I have no advice to give because I just never saw it and I never cared. And I probably always saw the parts that were good, like being able to use a bathroom without waiting in line. I just found really, well, I'm sorry, but men won't even understand that. And I also found times when the men wanted to help me, and I was perfectly willing to let them help me when it was something for me to do. And I realized that it was because I was a girl that they were willing to help me, right? There was just this one time when I was an undergrad, and I'd spent my whole summer trying to make this one germanium on gallium arsenide diode, and my hands shake so much that when I was trying to glue a piece of silver wire to it, it flew out of my tweezers onto the floor right where everybody soldered, right? So you can imagine this little gray chip thing with hundreds, if not thousands of pieces of little gray solder. So I'm down on my hands and knees because I had spent my whole 4 months doing it, so I wasn't going to let it go. It didn't work when I found it, but that's beside the point. And I'm down on my hands, and the first male grad student came in and asked what I was doing, and boom, he got down on his hands and knees. And by the end, I had 3 or 4 guys down on their hands and knees looking for this thing. And I even at that time thought, would they do this for a male undergrad student, or was it just because I'm a female, right? And so I would say that I probably always try to look for the positive in everything. But really, I went to a high school where the 3 girls won the math prize, the girls won the physics prize. Nobody said it was weird, And so I really just always kept going. I didn't understand why other women didn't want to do physics, and actually still don't really understand it. And so this is why I find it very hard. I understand that that I do represent it, you know, and so I try to do my best, but I don't think I'm a really good advocate for it. Did that answer the question? I went all around, but that's what I feel. I would have just, and I actually have to say that there was so much made of it on that day that I really thought it took away from poor Art, who had waited till he was 96, for goodness sakes, to finally get it, and Gerard. And I just thought, you know, they deserve it as much as me, and yet all the focus was sort of on me, and I just thought that was also sort of unfair.
Hi, yeah, thanks a lot for your great talk. I was just wondering, what do you find the most surprising application of your discovery?
Most surprising. Most surprising. I don't even know all the applications, so that's a tough one. Well, I still like, I mean, my favorite one is still going to be laser acceleration. And I have to say that just recently, Toshi Tajima approached me to work with him. And Toshi Tajima is the person who sort of invented laser Wakefield. And we're going to do it with my fiber laser that I'm hopefully developing sooner rather than later, to do it for medicine and do it small scale, hopefully with a fiber, you know, to go down into your body. So if it works, I think it'll be really cool. And if it doesn't, well, hopefully we have some fun trying. So I think that Gerard always talked about, we actually got to meet the Pope. This is the amazing thing about being a Nobel laureate. And I'm not Roman Catholic, but it's still amazing to meet the Pope. And we gave him a brochure. This is what Gerard's idea, because he said he was, and this is something he said during his Nobel thing, so I'm not sharing any secrets here, that he was going to dedicate his life to cleaning up nuclear waste. I'm still not sure that's going to work, but if it could, that would be lovely. Unfortunately, I think it works. We know it works one atom at a time. The question is, what kind of lasers are it going to take to clean up the tons and tons of nuclear waste? But if it works, a good one. But I'm just going to say the very first time, this is what most surprised me over all the years, was the first time I went to Clio and saw, I think it was Coherent, actually sell a CPA laser. That really sort of just floored me at the time, that this thing that I had found so hard to work with and almost never worked when I used it, right? Because let me tell you a story about when we put it in the New York Times that we had done this, and then 2 students from the University of Rochester wrote in the Rochester newspaper, and one of them was a political science student, so that one I can forgive. The other one was a mechanical engineer. And they said, look, they say they want to do atomic physics with it, but we know they want to blow up Russian missiles. And when, yeah, with our millijoule laser, let's just knock that thing down. And so we invited these 2 students over and set up. So it might have been when we had the 100 millijoules. I can't remember, but it was still not going to blow up a Russian missile. So we'd gone out and bought a little toy missile, and we're going to show that all we could do was pit it, 100 microns at a time. But when the students came, it didn't work. And then before Silong Chin came, I was going to do high order harmonic generation with the French group, and Louis Lamprey came for 6 weeks, and the laser didn't work that whole 6 weeks. So to me, the fact that Coherent had figured out how to make it work and turn a key, and it worked, I just found that truly amazing. It also said that we didn't have the job security. I can tell you that in the olden days, short pulse laser people really thought we had job security because we had to be intelligent, but we also had to be really good with our hands. And so we thought very few people can do this, or at least have the patience to do it. But now it's a turnkey thing. Let's go figure.
I guess I can probably speak for a large fraction of the audience when I say I can remember the moment when I realized that I guess I'm not going to win a Nobel Prize. But I'm speaking to you who's someone who did win a Nobel Prize for the work that they did in grad school. And I guess I'm just wondering, how important do you think it is to maintain kind of dreaming and optimism and things like that while you're being a physicist? Or do you think that it's sort of toxic to imagine that one day you could be winning a Nobel Prize? Or, I don't know, did you embrace the dream? yeah.
Well, I think that's very wrong to hope one day to win a Nobel Prize, because there's so many brilliant people, many of them in this room, that haven't won. And why not? I don't know, because they're just not as lucky as me. I mean, honestly. So I think you can just disappoint yourself if you're aiming for a Nobel Prize. So I think that's wrong. But obviously, you know, you have to keep going, because as I said, I started my PhD in '81 and didn't do anything successful until 1985. So I had 4 years of many failures. So you just have to keep liking it anyway and keep enjoying it. But it's also funny, because it's another story about making sure that when you give talks nowadays, you should always try to give a really good talk, because they're almost always being taped. I mean, this one, we forced people not to tape, but I gave a talk, I think it was a women in physics thing at the University of Waterloo, and it was taped. Now, I bet you 10 people watched the tape until I won the Nobel Prize. And then it wasn't even that it was taped and people wanted to see what else I did, but in that talk, which I had forgotten about, but my husband noticed everybody commenting on it all of a sudden, is that in the talk, I explained that Maria Gopimer did the multi-photon thing, and I talk about how I said, you know, she did Nobel Prize-winning work, I think even for grad school, but she didn't get the Nobel for it. She did Nobel Prize-winning work, but it was, she didn't get paid to be a scientist until she was at Argonne. She followed her husband and always did other jobs or what have you, and did research just for the heck fun of it, right? And so when I'm speaking about it, I said, look, you know, times are changing for women in physics, because I haven't done Nobel Prize-winning work, and they're paying me, right? And that's what caught, that line just caught, you know, and so since winning the Nobel Prize, now 4,000 people have watched it. I keep thinking, I hope that talk was good, because honestly, who needs anybody watching you give a so-so talk? But anyway, be careful what you say. But yeah, you never know. You never know if you're doing Nobel Prize-winning work.
All right. So we are going to end the questioning session here, and please, everyone, help me thank Donna again for a wonderful.
Thank you.